好，那今天很高兴我们可以邀请到就是 Mount Sinai School of Medicine 的黄冠霖教授来我们这边给我们演讲。那黄教授呢，他其实是台湾出生长大，建中毕业，但是他大学呢到美国的 Connecticut 念 Wesleyan 的 University， 然后后来在这个 WashU in St. Louis 拿到这个博士学位。那现在呢，就是黄教授主要的研究方向主要是在做 Precision Medicine， 那包括这些 Omics data， 那还有也在这个这个 Professor 就是 Genetics and Genomics Science and AI in Human Health 的 Associate Professor。那是要非常谢谢黄教授，是因为我们过去2年其实都有学生到 Mount Sinai 去做这个暑期的研究活动，那学生的反馈都非常好，那也很谢谢黄老师愿意带我们的学生。那今年我们都还会持续继续送学生过去，甚至未来还希望跟Mount Sinai的医学院有更多的这些合作。那我们今天就很欢迎黄教授来给我们这个演讲，欢迎。
谢谢杨老师，然后也谢谢大家的邀约。那我先用中文讲，然后讲到研究的部分用英文讲，让大家可以认识我一下，然后大家也可以等一下可以有一些时间问问题。那杨教授说了，我们 Mount Sinai 呢是纽约某一些 metrics 最大的医院，然后我隶属于他们的医学院之下。你如果看纽约有个中央公园在这边，那这边是东边，这边是西边，我们就在上东区，这边是医学院。那当然我们医院是遍及纽约市各地。那如果你有机会呢，尤其是秋天来的话，这边叶子变色就会很漂亮。夏天也不错，夏天可能太阳7、8点才下，然后天气比起台湾也舒服很多。所以去年阳明来访问的同学都还蛮开心的，就觉得他们夏天晚上可以去玩啊，然后有很多活动啊，在纽约还蛮好的。
我念博士班是17楼，在这边。我是上课下课10分钟我都回去做实验，然后晚上做到1、2点，所以这个是上东层。那夏天可以在这边打叫什么排球，然后那个大都会博物馆在这边，这边叫做 Museum Smile。OK， 大概是这样子吧。好，补充一下。
对，老师说得很好。大都会博物馆离我们10条街，我大概每个月都会去一次。
那个
没有用。
Lincoln Center 应该是在。
Lincoln Center 在这边，在西边，靠近城市这边。对。好。我要对这个，老师，我要对。对着，还是我按到什么吗？
那你的办公室在哪里？
我办公室在刚刚那张图看不到，就是在这边104街，那边在大概100街左右。对，那我在台湾历程呢，我觉得我跟阳明特别有缘，因为我住在北投，从小在北投长大，然后当然我高中同学也有人来阳明，那你就看得出我的活动范围。因为我从小练游泳，后来去百灵，然后到建中就觉得其实有点太远了，所以就活动范围我通常都在北投，在骑脚踏车，在家里附近。那后来又当替代役在竹围国小，也是在北投关渡区。那我可能还是要用这个。那大学的时候呢，那时候我本来是在台湾考试，然后美国我就只申请了一个奖学金。可是也因缘错差，就那个奖学金每年给1到2个台湾学生，然后就去了一个在台湾没有那么有名的学校，叫 Wesleyan University。可是我觉得这个他们美国有一些教育体制还蛮有趣的，像这个是一个 liberal arts education， 所以我们学校本来是相对于讲硕美龄夫人她念 Wellesley 相对的难小。那这种学校它的优势就在于它的学生很少，可能跟医学系有点像，可是每一个课里面教授跟学生比就很高，所以比如说我后来上了很多艺术课，那我的课可能就是在纽约真的是艺术家的老师，他每个星期来我们学校可能2天3天，然后到最后最高门的课可能就只有2、3个学生，所以就可以 做很多比较像 project based， 而不是只是念书的东西。那当然我在那边也做了一些 East Genetics 的研究。那后来呢？后来到 PhD 的时候，我就到美国中部，这个也不是一个台湾那么多人知道的学校，因为常常会有人把 University of Washington 在华盛顿州的西雅图的学校跟 Washington University in St. Louis 搞混。Washington University in St. Louis 在 St. Louis 就是在美国正中间的一个学校。那它其实在 Human Genome Project 跟后来 Genomics 算是一个非常重要的 hub， 就是仅次于 Broad Institute， 它是 sequence Human Genome Project 最多的地方。那当然最重要的就是现在，我在 Icahn School of Medicine at Mount Sinai 待了超过6年了。那我们学校呢，体制其实非常非常庞大，只是它没有很有名的另外一个原因，在台湾，因为它没有本身的大学，它是一个很好的医学系统，也是一个很强的医学院，可是它没有大学。那你就可以想象，这个医学院本身就有300多个实验室。那在美国呢，因为大家的薪水比较高，然后研究比较花钱，所以经费尤其重要，就是要 NIH funding。那我们学校在 Neuroscience、Genetics 跟 Microbiology 的 funding 都非常非常的高。好，那我讲完自我介绍的部分，等一下还可以回答更多问题。我讲一下我们实验室在做的事。那我们都知道，在 Precision Medicine 呢，现在有一个新的机会，就是越来越多人可以有自己的 Genomic Sequence。因为现在 genome sequence 越来越便宜，甚至到$200都可以做得出来。那可是因为我们每一个人的 DNA 蓝图的 genome 都不太一样，所以呢，我们每个人得到一些 disease 的 risk 跟每个人的 drug target 可能也不太一样。那我们实验室就是尽力在这里面扮演一个小角色，看能不能把它做得更好。那现在呢，另外一个新的机会是，现在除了我刚刚说的 genomic sequencing cost 越来越低之外呢，我们开始有很大量的 genomics data。另外一个呢，是大家也都知道，在 AI 技术方面有非常非常高的突破。所以你可以想象，如果我们可以把这2个重要的 technology wave 结合在一起，那它应该就会有很多 breakthrough 跟 innovation。那我们实验室呢做的很多不同主题，就在跟这些 genomics data、large data 还有 machine learning AI application 有关。那我今天主要讲的是我们在 precision 跟 AI driven genomics 的 project 上的应用。那我们也有用在一些像大家知道 GPT 是 large language model， 可是你也可以想象做一个 DNA、RNA、protein language model。那甚至呢，这些 prediction 有时候你可以结合其他的医疗资讯，像是在血液里的 biomarker 啊，或者是 pathology。那这些其他方面，我今天可能就比较没有时间讲到。好，从现在开始我改成用英文讲，希望大家 OK。So today's talk, I will focus on developing state of the art. Now in the machine learning world, people like to call it SOTA, AI variant effect predictor, and I will talk about why that would be important. And you can always build an artificial intelligence, but in the medical world, it means nothing unless you can implement it to improve population health and to help improve individuals' medicine. And so, second, we will talk about how we implement this in populations. And then third is some preliminary thought about how to translate this into the clinic. And the main caveat is I'm not a PhD, and there are other doctors in the room, so I'd love to hear from all your advice too. And the first part of the work, developing a state-of-the-art variant predictor, is done by Megan, who was a PhD student in my lab that just graduated. Okay, so why do we need AI for genomics? If you sequence your genome, what would you find? Does anyone have an idea? Like any students take a guess? Like how many variations, how many spots of a genome may be different from you and the reference genome? Does anyone have an idea of percentage or like numbers, or want to take a guess? Millions. Okay. So it really depends on who you are and what the reference genome is, right? And there's a diversity issue. But if we focus on just the coding part of the genome, which is just like less than 2%, then you will find tens of thousands. So I guess if you scale that by 50, I think millions is about right for what you find in the whole genome. But I think most of the non-coding space are still an active area of academic research, and most of what's applied is in the exomes. But even if you look at the exomes, and if you put yourself among 1 million people that are sequenced, which we actually now have a database of from Regeneron, then you can actually find out among those 40% are unique to yourself. And the opportunity and challenge in that is that some of those mutations might dictate whether you will get a disease or not, and most of them won't matter for a given disease, right? So some of those examples, like BRCA1 mutations. But you can imagine the problem with most of these important genetic variation being so rare is that statistically or clinically, it's really hard to classify and make all these genetic information clinically actionable. And so in the universe, among the known mutations that we have classified and can classify as pathogenic, is very little compared to what's possibly predictable as pathogenic variants, right? So you can imagine that the AI predictable pathogenic mutations and the real pathogenic mutations are actually a much larger set than what's known as pathogenic variants. And how that matters to individual health, I like to just talk about one story. I don't know how many people here might know Chris Everett or follow tennis. So maybe the problem of Chris Everett is she's like a last generation tennis legend that has won a lot of Grand Slams. And she and her sisters are both tennis professional players. But her sister, unfortunately, when they're older in age, they went to do a tennis clinic in Singapore and suddenly feel unwell. And a week later, the diagnosis come out that she has ovarian cancer, which is also a very troubling cancer because most of the time it's discovered pretty late and the patient survival prognosis is really bad. So unfortunately, her sister passed away. But because of her sister's ovarian cancer, you can imagine that quite a fraction of ovarian cancer are caused by inherent genetic variants, like those in DNA repair genes BRCA1 and BRCA2. So Chris Everett also got genetic testing. The problem is that at that time, she got a report back. They found a variant of, I think, BRCA2 in her as well and her sister that is unclassifiable at the time. So that becomes really tricky because an unclassified variant could actually be a pathogenic variant or it could mean nothing. So at that time, they decided to just keep an eye on it and not do too much. And what happens is that 2 years later, there are more research that are done, and new research actually suggests that that variant that's previously unclassifiable is actually now deemed to be likely pathogenic. And so they quickly give her the updated report, and because of that, and because she's already older in age, she decided to take preventive action and remove her ovary. And the crazy thing about that is that the doctors actually found when removing her ovary, there is already a stage 1 ovarian cancer, which really thankfully most ovarian cancers are not found that early. And so she really think that, because of that genetic report and that being updated, and then also because unfortunately of her sister passing, that she's able to realize and prevent her cancer. And she really think that genetics and her sister has saved her life. And so, I think it really is worth it to think about, can we really use these AI predictable mutations to improve our genetic diagnostic? Okay, so how do we go about building a state-of-the-art variant predictor? You can imagine that actually being able to predict what every base of your genomic sequence change is actually a very important research area, and there are actually a lot of other people that have tried on this and that reach different level of results. Our unique insight is that a lot of people have leveraged a lot of evolutionary based information because those are really easily accessible on a large scale, a lot of people have started leveraging a lot of structural innovation, because you can imagine Google's AlphaFold algorithm can now predict a lot of protein structures aside from those that already have experimental structures. And our unique insight is we're going to leverage more functional information, as now there's a lot of large-scale functional screen of saturated mutagenesis of a lot of proteins. And if we can curate those well and use those meaningfully in training, we might not have a more sophisticated model than Google DeepMind, but we may actually be able to more meaningfully learn from a stronger functional label. And so that was what Megan was able to achieve. As you can see here, that we compare the performance of our algorithm called Maven to the other state-of-the-art algorithm, including AlphaMistSense, which was published by Google DeepMind in Science last year, and ESM1B, which is based on Meta's algorithm. And our model architecture is less sophisticated than those two models, but what we uniquely have is we have stronger functional labels of experiments. And so obviously, if we measure this against other experimental protein data that we didn't train on, we perform better. But what's striking is not just our model's prediction on predicting other functional variant data, but our ability to predict other genetic variants. And so this is one task that a lot of these newly developed AI models try to benchmark against, which is to find mutations that are in de novo cases of developmental disorder, which means that sometimes when a kid develops a new disease that his or her parents don't have, we thought that this kid might have a different mutation that are not in his or her parents' genome. And so in doing this task, you can see that our algorithm, Maven, achieved the top performance in 2 out of 3 developmental disorder cohort, including autism, cardiovascular disease developmental disorder, but not the last cohort where AlphaMistSense still achieved the last performance. So we think because of that, we really can leverage a unique functional insight. And I think that is very important to think about when you develop AI model nowadays, because now a lot of people are interested in a lot of corporations with really strong teams at developing AI, but really think about where is your unique strength and where your model might complement other models.
What's DNM stand for?
The de novo mutations.
Okay, thank you.
Yeah, so that's the mutation that we're trying to find in these tasks. Yeah. So the lessons we learned from building Maven is that we really pay attention to these strong labels. And the other thing that is a little more biology involved that allow us to do a great job is that evolution, which a lot of other state-of-the-art model leverage the most on, is related to pathogenicity, right? Because you can imagine that, say, if you have a mutation that causes breast cancer, then on a longer evolutionary time span, that mutation is unlikely to get really common, because people who have breast cancer are more unlikely to reproduce and pass that same genetic variant on to the next generation. But they're not always the same. And this is especially important, for example, for some other later onset disease like neurodegeneration. And so for example, in dementia and Alzheimer's, there's a really common ApoE4 variant that has other things to do with lipid metabolism that increase risk of Alzheimer's a lot. But it may not have been so evolutionary selective against in previous evolution. And lastly, all these does not directly equate function either, because a DNA damage repair function, for example, in the BRCA gene may have to do with whether a person is likely to accumulate more other mutations and acquire breast cancer, but that's not always the case either. And then, so lastly, also because of this, we realized one of the hardest things in the project is that everyone is so excited about building their own AI. And I think you can see this in the general language model LLM world as well. So many people are building AI. It actually is a really important thing to think about what is actually a meaningful task to benchmark the AI against, because everyone's AI is trained on different stuff and it could be good for different stuff. But if I were to ask you, is ChatGPT better as a doctor, or is Gemini better as a doctor, or is perplexity as a doctor. It's actually a hard question to answer, and having a really standardized and universal testing platform is really important. And in fact, this is a project that the previous Yang summer students, Ian and Claire, work on. Okay, so now we have built an AI, we have tested against other people's genomic AI. But as I've said, it's important to think about how do we actually bring this to a large amount of people to see what benefit it might have and might not have, and identify people actually with high risk, like Chris Everett, right? And so this work is done by Abkadir, who was a postdoc in my lab that started his lab in Turkey a year ago, and Rita, who is actually a graduate from NTU and started working in my lab a year earlier. So in motivating this, I want to talk about this famous example in the AI world of what could be a good and what could be a bad scenario. I wonder if anyone has heard about this story of AI paperclip factory, or like this might be a little more niche, self-replicator machine talked about by the mathematician John von Neumann. Has anyone heard these stories? Oh, okay, that's great. This story originated from this mathematician's theory that when you have any kind of cell replicators, it is very dangerous and you have to really watch out for it. And Nick Bostrom is a machine learning scientist. He wrote this book, Superintelligence, where he gives the example of a paperclip factory. So, AI could be really good, could be not as good yet, right? But imagine that we are at a point of time in history where AI is getting pretty good at doing some work, right? And so, the boss for the AI paperclip factory is really happy that, I now make an AI that can just make paperclip by itself. So then it's great, right, for the factory, because you can have really large production, you have no cost, etc., and everyone can just rest like a cat, not having to work. However, sometimes people worry about these scenarios, because what if all the AI want to do is to make more paperclip, and that actually sacrifices a lot of things. Maybe the AI will decide, all the metals in the world should go to making paperclip, so I will melt all your cars, take away all these resources and start doing breaking down environments to just make paperclips. Then maybe you can argue that, maybe I have these protective mechanisms, maybe we'll be fine in the end. But you're only at a point that AI, if they're able to self-replicate and get smarter, it might lead to an undesirable outcome, right? Like they can make everything into paperclip, and at a point you actually sacrifice your own human benefits. So I think it's especially important to think about AI, especially in the context of healthcare. And now there's more people dealing with this AGI, general intelligence problem. I don't think we're there yet, but I'm just thinking about it in a medical context, right? And so in machine learning, even in Machine Learning 101, you think about what your model optimized for. And I think it's a question that now, especially when a lot of people are more focused on sophisticated architecture, they neglect the importance of thinking about what is the thing you optimize for. In supervised machine learning, it's pretty clear, right? Most of the time, you have a function that you're learning against, and most of the time, you are trying to minimize some loss. For example, in this case, the difference between your predicted y value against the real observed y values. And this could be into some kind of function. But even on supervised learning, you have to think about your model is going to inherently learn all the structures in the trained data. And so this, what is being optimized for and how it's being optimized, become even more important. And so, in the example that we gave on Maven and recently Google's Alpha Missense, you can see that all these models are really, really good in silico, right? They are all like 95% in silico, and it almost doesn't matter to say which model you pick or not. But I think the real test really come into whether you can actually make it work to people, right? Because let's say previously you go see a doctor, the doctor say you have a BRCA1 variant, like Chris Everett's case. Then maybe you can say, okay, I want to be proactive. I want to think about removing my ovary early. But if AI predicted to say you have a BRCA1 variant, then at which point do you feel like it's okay to trust it, right? Would you trust it right now? I think that's important questions to wrestle with. And the other important thing that we want to consider in this is that a lot of previous genetic studies are done in mainly Europeans, and that make the data being really biased towards finding European genetic variants, especially given genetic reflex of populations, migration, and later history. So it's important to also have a cohort that really consider a lot of other ancestries. And I think a lot of doctors work here also focus on sequencing for Taiwanese population, for example. That will be very important to improving our health. At Mount Sinai, one of the unique strengths we have is that we have this really diverse biobank compared to a lot of other sequence cohort out there. And we have this strength because compared to a lot of elite academic center in the US, we're located in New York City, which is one of the most diverse area in the US. And so in our cohort, we not only have 1/3 European, but we actually have almost 1/3 African ancestry individual and another 1/3 Hispanic and Latino ancestry individuals. And if you look at their genetic data on a common PC plot, you can see a wide range of diversity in this cohort that we use. And importantly, this is expanding to the Sinai Million Health Program, and we're really excited to start analyzing this data. So we'll have 200,000 patients' genetic data coming by the end of this year, and hopefully to reach 1 million by 26, 27. Okay, so now we have the data, we have the model. How do we go from there to actually implementing the AI in the population? Long story short, that when we actually try to implement the leading model at the time before we developed Maven, Google's Alpha Missense. Google's Alpha Missense already derived a threshold of using their model to find so-called pathogenic variants based on all the in silico benchmark they did. But when we directly apply their threshold, we find a really troubling sign that if we look at the 28 cancer secondary finding genes released by ACNG, which include genes like BRCA1, BRCA2, that in the guideline, physicians are supposed to report back to patients because these genes are so important and actionable. We actually find that in our biobank cohort, almost 8% of patients, even the controls without any family history, have a Google Alpha Missense predictive variance. And so not only is this in the US healthcare environment not implementable, just because in the US the healthcare is slower, the genetic counselor is not going to be able to even report back and discuss with all these patients, but also there probably is a lot of false positive or a lot of patients whose risks are not comparable to current pathogenic variants at all. So we did a nice job really tuning the different threshold and the way to use Alpha Missense until we find a more satisfactory threshold to find pathogenic variants. And what we find after that tuning is actually pretty meaningful because now, if you remember back to the circles we were looking at, the ACNG classifiable pathogenic variants, according to the guideline, reported back to the patient, is still a really little percentage. And so for even most cancer types here on y-axis, each group is the cancer type to that tissue that we look at in our biobank cohort. Most of those cancer types patients who have a pathogenic variant is lower than 3% and mostly around 2%. Interestingly, the controls even have about 2%, but that corresponds to what we know about these pathogenic variants odds ratio. But when you look at the tuned AI threshold of predicted deleterious variants, you see that increase the fraction of patients we identify by quite a bit, mostly over 100%. So you see that for many of these cancer types, they have 4% of those patients identify having one of these important pathogenic variants that they have to know if a physician has done sequencing for any disease, even non-cancer disease, because they are important secondary finding genes. And also for their families who might also want to get tested. And so we really think that this really change completely how we think about clinical genetics and genetic testing. There's a lot more patients to be found. Perhaps like when Chris Efford first got a genetic report, she didn't found her BRCA variants, but now with AI prediction, she would have been. The important thing is we also want to establish that these patients actually have the same cancer risk as the patients carrying already known pathogenic variants. And so in doing this, we corrected for the clinical covariates and used the standard logistical regression model to find the odds ratio of these variant carriers for various types of cancers. So for example, this plot is quite convoluted, so I won't go into detail. The BRCA1, BRCA2 variants shown in red have a really high chance of getting breast cancer if you look at pathogenic and likely pathogenic variants. But for this group of patients, they not only show increased risk of breast cancer, perhaps a little less than pathogenic variant carriers, but we also established that they have risk for other cancer types as well. Here, an obvious caveat is that there are just more of AI predicted variant carriers, so there's more statistical power to identify the association. But what we find in general is that once we tune these thresholds carefully, the AI identified variants carriers actually have equivalent or higher cancer risk sometimes than the pathogenic variant carriers. And that really is the neglected set of patients that we are not currently giving the report back to that can really change how we think about genetic testing. And so what we learned from this exercise of implementing the genomics AI to a big population is that even if you have a really good AI model, it likely won't work out of the box for especially a biomedical application, right? I think that is the same if you were to upload a radiology image or if you were to ask GPT directly a medical question. It's pretty good, or maybe it's not that good, but you definitely can't just use that without any tuning as a doctor. And so in thinking about that, I think in every domain, there's a lot of task-specific expertise or benchmark that you know the model has to reach. And so in our case, for example, we know that in our benchmark, these patients in genetic tests really have to show much, much higher risk for a physician wanting to report back to the patients. And so we are needing to actually use these additional data to fine-tune. And most ideally, you don't want to have any data shift problem, which means that your data that you use in training or tuning is different from the population you want to actually test it on. So the best in this is actually you actually have population data that you actually want to implement your AI in. And so there's a lot to think about and a lot to work on that we and our collaborators are working on, is to really bridge the gap between these advanced AI models and really big population evidence, which is what we have shown. And we have started talking to quite a bit of physicians, clinical geneticists, and start implementing on a small scale, how do we moving this to the clinic. And so this part is more exploratory because I think there's a lot of different ways to think about this, and different physicians we talk to have different ideas. But just a rough idea now, just to think about what is the state of the art that is being reported there for a given genetic test. You have the variants that are reported by the ACNG guideline. And so if you're an individual that went to get sequenced, you get one of these reports. But the problem here is that you could have this variant or not have a variant, but you could actually have an AI predictive variants that we talked about, that AI could actually give really strong evidence that are not reported right now. And the other key problem is that the current clinical guideline is very qualitative, right? So it just calls a variant pathogenic or likely pathogenic. But maybe for a pathogenic variant, and there's some really nice work in collaboration with our collaborator, Rondo, to show that even for a lot of pathogenic variants, carriers, among 10 people who carry the gene or variant, there might only be 4 of them that actually develop breast cancer. And the other pathogenic variant might have 8 out of 10 carriers that develop breast cancer. But those two could be reported the same right now. But they could mean very different things to how a patient might think about their disease risk. So I think with large-scale population data and with AI, we now really have the opportunity to change that from a qualitative to a more quantitative prediction. And also, we're really able to really disentangle each base pair of changes. A lot of those are not going to be seen in any other people that have sequenced in the public domain so far, instead of just relying on gene level odds ratio. So for example, now people know BRCA1 carriers have a certain amount of risk that is based on the carriers of a whole bunch of variants in BRCA1 combined. But imagine if we can reach that at a variant level precision, then that information is much more accurate and actionable in many cases. And the key question is how. I think a lot of this has to also do with economic incentive. It really varies by the healthcare system. I think in the US, incentivizing diagnosis, especially risk diagnosis, is a really hard question, and there's actually a lot more resource, for example, in drug development. That varies countries by country, healthcare by healthcare system, because of how the payer-provider system is structured, and that also vary because of how genetic counseling and how genetic report are delivered back to the patient. So I think there's a lot of creativity that can be utilized here in thinking about this for different disease, for different genes, different use cases. I think that's the end of my talk. I think I really like these quotes that I want to share with everyone, especially in Taiwan, because everyone knows a famous scientist like Einstein, and I think a lot of science is about really good execution, which I think the Taiwanese education has taught us all really, really well. At the same time, I think it's important to think about how you imagine to be a better world or important thing you want to realize. And Einstein has said that, but it is nothing that's exclusive to a Westerner. Back a long, long time ago, Hu Shi say, actually, we are pretty good at part of 小心的求证, but then I think we also should think about how we 大胆的假设 as boldly as possible to do ambitious projects. Aside from that, I have a quick plug to this nonprofit that I co-founded, Open Box Science. Basically, it is webinars. Instead of being exclusive in a school like this, in the talk that I'm giving now, it is a talk that's open to everyone in the world. And actually, me and my friends and our co-founders, we have hosted over 200 talks. And the uniqueness of these talks is not just like older people like me talking, but also we try to invite the first authors who actually did the work. And one of the selfish reasons of me starting this is I realized for my own lab's journal club, sometimes the quality is not as good if the student didn't prepare as well or they didn't have as much time. But if you invite the first authors, they almost always give a brilliant talk on the work they did because they're the one who did it. Most of the time even better than the professors could. So there's a lot of talks on this that you can check out on the website, on our Slack, or on Listserv, or you can just Google search Open Box Science. We especially have more talks in neuroscience because one of my co-founder and good friends is a neuroscientist, and genomics and immunology. And then lastly, I think I want to leave more time for discussion, whether about personal life in New York, or how it's like studying abroad, or doing research in the US, or any part about research or any other questions. I'm happy to answer everyone's question. Thank you.